This is an installation of long underground buried pipeline for which sacrificial anode type cathodic protection system is being provided. At this location, 3 numbers of magnesium anode is being installed. These are the magnesium anodes. Let us see cathodic protection calculation for calculating number of anodes and anode distribution along the buried pipeline.
Suppose we want to protect one 16-inch 2.5 kilometer length of underground pipeline by cathodic protection system using sacrificial anode, magnesium anode. So, pipe length equals to 2.5 kilometer equals to 2500 meter. Pipe size equals to 16-inch. OD equals to 406.4 mm equals to 0.406 meter. Now first is we have to calculate surface area of this entire 2.5 kilometer long UG pipeline. So line surface area SA equals to pi into OD into L equals to 3.14 into 0.406 into 2500 equals to 3187 meter square. Then second step is current density. Current density JC equals to 0.3 milliampere per meter square. This is as per ISO 15589 part 1 for wrapping and coating. This figure is for wrapped and coated pipe as per ISO 15589 part 1. This is JC, current density. Then we will have to calculate total current demand in ampere to protect the entire UG line. This total current I total equals to SA into JC by 1000 into 1 plus safety factor 25%. So total current demand I total equals to this SA is 3187 meter square into 0.3 by 1000 into 1.25 equals to 1.195 ampere. Where I total equals to total current demand in ampere, SA equals to pipeline surface area in meter square, JC equals to current density of coated pipe, SF equals to safety factor equals to 1.25. Then fourth equation, we have to find out resistance of single anode RH. As per Peabody's Control of Pipeline Corrosion Handbook of NACE, means National Association of Corrosion Engineers, RH equals to 0.00159 divided by LA into rho into 2.3 log 4 LA square plus 4 LA square root A square plus LA square divided by D into S plus S by LA minus square root S square plus LA square divided by LA minus 1. This is the equation where RH equals to resistance of horizontal anode to earth. Rho equals to resistance of backfill soil. Say it is 2500 ohm centimeter as per soil test report. Ohm centimeter. LA equals to length of anode equals to 750 mm equals to 0.75 meter. D equals to dia of anode equals to 200 millimeter equals to 0.200 meter. S equals to twice depth of anode underground, that means about 4 meter. Magnesium anode looks like this. This is the magnesium anode and this is steel strip. and this is backfilled gypsum 75% plus bentonite 20% plus sodium sulfate 5%, and this is the cotton bag, and this is the cable, anode cable, and overall dimension of this magnesium anode is 750 millimeter and diameter is 200 millimeter. This is the entire assembly of sacrificial magnesium anode. So RH equals to 0.00159 divided by 0.75 into 2500 equals to 5.3 into 2.3 log 2.25 plus 12.2 divided by 0.8 plus 5.33 minus 5.4 minus 1 equals to 9.56 ohm. Now, fifth equation, we have to calculate interference factor IF using Peabody's control of pipeline corrosion handbook. IF equals to 1 plus 2LA divided by E ln 0.656 N divided by ln 8 LA by D minus 1, where IF equals to interference factor, LA equals to length of anode equals to 0.75 meter, D equals to dia of anode equals to 0.2 meter, E equals to spacing between anode equals to 1 meter, N equals to number of anode, say 1. Using this equation, IF becomes 1. Then sixth equation, we have to find out resistance of ground bed RG. RG equals to IF into RH divided by Ng equals to 1 into 9.56 ohm divided by 1 equals to 9.56 ohm. Ng equals to number of anode in ground bed. Then seventh equation, anode current output IAF. Anode current output is the difference in potential between the anode material and steel polarized to protection divided by the resistance of anode in the electrolyte. IAF equals to EA minus EP divided by RH. EA equals to anode potential equals to 1.7 volt. EP equals to protective potential. That means potential for the cathodic protection, that is 0.85 volt, and RH equals to resistance of single anode equals to 9.56 ohm. So IAF equals to 1.7 V minus 0.85 volt divided by 9.56 ohm equals to 0.09 ampere. Then we have to find out number of anode. That means number of sacrificial magnesium anode. Anode length is 750 millimeter. Anode diameter is 200 millimeter. Number of anode is calculated by two ways. One is 8.1 number of anode by current Ni. Ni equals to I total divided by IAF equals to 1.195 ampere divided by 0.09 ampere equals to 13.3 numbers. Say 14 numbers. So based on current requirement, we require 14 numbers of anode to protect this 2.5 kilometer length pipeline. Then in another method, 8.2, that is number of anode by weight, that is NW. Anode dimension is anode dia equals to anode dia equals to 200 mm, anode length equals to 750 mm, anode net weight equals to 14.5 kg, and anode gross weight equals to 31.8 kg. This anode data is received from the vendor. Then number of anode required to protect the pipeline is calculated using the formula M equals to 8760 into I total into TDL by U into epsilon. This equation as per ISO 15589 part 1, where M equals to total net anode mass in kg. 8760 is hours per year. TDL is design life, say 20 years. I total equals to total current demand. U equals to utilization factor equals to 0.85 as per ISO this, and E equals to electrochemical efficiency equals to 00 Ah per hour. This is as per this code. So M equals to 8760 into 1.195 into 20 divided by 0.85 into 1100 equals to 223.9 kg. So total required number of anode by weight equals to M divided by MA equals to 223.9 divided by 14.5. This MA is weight of each anode, 14.5 kg equals to 15.4 numbers, say 16 numbers. So required number of anode from current requirement point of view is 14 numbers, and from weight it is 16 numbers. So hence selected number of anode equals to 16 numbers. Now coming to anode distribution. Say this is the entire pipeline of 2.5 kilometer. This is 2500 meter or 2.5 kilometer. So we provide 3 anodes here at 250 meter distance. Then we provide 2 anode after 400 meter. Then we provide 3 anode after 400 meter. Then 3 anode, then 2 anode, then 3 anode, like this. So total number of anodes 3, 3, 6, 2, 2, 4, 10, 3, 3, 6. Total is 16. So in this 2.5 kilometer length, we can split the anode distribution like this. 3 this side at 250 meter from this side, and 3 this side at 250 meter, then at a gap of 400 meter, and 2 anode here, 2 here, 3 here and 3 here, like this. This can be the anode distribution. And in each anode distribution point here, test point will be there. This is test point, this is test point, this is test point, test point, test point and test point. So at 1, 2, 3, 4, 5, 6, at 6 places we are providing anodes. So our test points will be at 6 places. 1, 2, 3, 4, 5, 6. Now this is the elevation view of underground pipe. This is UG pipeline with anode installation. This is anode 1, this is anode 2, this is anode 3. From pipe bottom, this requirement is minimum 300 mm, and in between two anodes, this requirement is minimum 300 millimeter. And this is the test point, and this is JB, junction box, and this is test point. To the test point, cable goes like this from this anode, and this anode and this anode are connected. Cable goes to these two anodes like this, and another cable comes from the JV to protect the pipeline like this. Here thermite welding is there. This is the arrangement of anode location in UG pipeline and junction box and test point. In this junction box, periodically we can measure the potential of these anodes and potential of the pipeline being protected.